Hello. My name is Robert Brown, the discoverer of Brownian motion. Leroy has hired me to talk to you about Brownian motion and random walks today. He says I have a good voice for explaining physics. I'm not sure what he means, but as long as I get my paycheck, I don't care. So let's get started. What you are looking at is a collection of tiny fat droplets roughly 1/1000th of a millimeter wide, suspended in a water-based solution. In other words, you are watching milk under a microscope. The droplets do not sit still as they would on their own. They are constantly jiggling in random directions, and never slow down or come to rest. And yet, they do not jiggle in place. If you focus your attention on one particular droplet and follow its trajectory over a long time, you will see that the particle actually drifts slowly away from where it started. This irregular, erratic motion is named Brownian motion, in honor of myself. I first discovered this phenomenon in 1827 while studying grains of plant pollens suspended in liquid under a microscope. At the time, I thought the pollens might be moving because they were alive. We now know that this is not the case, and we will discuss a physical explanation now. This simulation from physicsanimations.com shows a relatively large molecule, in blue, surrounded by many smaller particles from the ambient water, in red. Due to thermal energy, these smaller water molecules are zipping around in random directions and colliding into the blue molecule. These collisions are very numerous and very frequent. In fact, a pollen grain immersed in water will experience about 100 trillion collisions per second. Just how much is 100 trillion? Imagine if the new Star Wars movie were cancelled tomorrow. 100 trillion is approximately the number of letters and emails Disney would receive from angry fans. As a result of this constant bombardment, the blue particle experiences a random force, whose direction and magnitude vary at every instant in time. This random force results in the constantly changing, erratic trajectories that we see. The mathematical theory of Brownian motion based on this picture of colliding molecules was worked out in 1905 by Albert Einstein. Now that we have an understanding of the physics, let's examine how to quantify the trajectories. To this end, we will explore something called a random walk. Imagine a drunken sailor standing outside. Every second, he takes one step of length L, but he is so inebriated that the direction he moves in is chosen at random. The question is, after 100 steps, how far away will he end up from his starting location? As you can probably imagine, this problem is very similar to the problem of Brownian motion, except that we are taking one step every second instead of continuously moving. Now, we cannot say definitively where he will end up because his actions are randomly determined. His trajectory could be a straight line, or he could even move in an east-west pattern, never leaving the vicinity of his starting location. Both of these are possibilities, if extremely unlikely. However, it is possible to say something about where he will end up on average. That is to say, we can make a good guess about how far away we expect him to have moved in most scenarios. For our sailor who took 100 steps, he will on average end up a distance 10 times L away from his starting point. In general, after he takes n steps, he will end up a distance square root of n times L away. Again, this is only an average, not a guarantee. In these sample trajectories done by Leroy, you can see that there is quite a bit of diversity in the start-to-end distance. Since the Brownian motion is essentially just a continuous random walk, we should expect a similar-looking formula to describe the average drift distance. This formula can be found by solving what is called the Langevin equation. Though it may seem complicated, The Langevin equation is nothing more than the old formula, force equals mass times acceleration, where the two forces acting on the particle are, the random force mentioned previously, and the drag, which is the resistance of the fluid to having a particle pulled through it. Drag is a combination of several factors including the shape of the particle and the viscosity of the fluid. After some calculation, the drift distance can be seen to depend on the temperature and the coefficient of drag. The time plays the role of the n from the random walk, which makes sense because the number of steps taken in a random walk is proportional to the amount of time that has passed. So that's Brownian motion in a nutshell. Speaking as a scientist from several centuries ago, I am thrilled that my discovery has found modern applications in so many disciplines, from the chaotic oscillations of microscopic objects to the fluctuations of share prices in the stock market, though I am told that the latter may actually be less random than we think. As for Leroy, he apologizes for his lack of video editing skills, but he hopes you learned something regardless. Thank you for watching our video, and have a good day.